Hello, campers. Hello, thank you. Yes, happy Valentine's Day, everybody. Yeah, we don't celebrate Valentine's Day in my household. In addition to my feelings about it being a manufactured greeting card holiday, I waited tables all through high school and college, and Valentine's Day was the worst day. So just please do me a favor, if any of you would like to share your love with your partner, your friends, whomever you want to, don't go out to eat tonight, okay? Just don't. Just don't. Because you know what you're going to do? You're going to wait 3 hours for dinner, and you're going to be starving and cranky, and you're going to get like a plate of lukewarm fettuccine alfredo for your trouble, okay? Just don't. That's my public service announcement. Find some other way to share your love. Or your hatred, you know, whatever. Is there any sort of anti-Valentine's Day celebrations going on? Teresa, you're grinning awfully wide.
No, I don't do Valentine's Day either.
Yes, amen. So, yeah, sorry, I don't have any candy to hand out or anything. I'm sorry, I just didn't. So, but I do have homework help, if you'd like that as a present instead. So, a couple of you have emailed questions, and I said, can we talk about that in class? And I think, Teresa, yours was one of them. You want to think about it? Okay. I had some questions about how to use fittest, and so I wanted to point out a couple of things with respect to that. So I just, the example 2, the accelerated time models, I realized that the code in this handout is a little bit older, meaning that I hadn't gone back over it with my same level of things I'm watching for to help you with your homework system. In this example, I had left off this IC option right here. That's the thing that allows you to save your info crit table to do the fit test. So you have to have these 2 little letters. It doesn't matter where you put them, so long as it's in this proc mixed line. I also used to have an option in here called no it print, which is the thing that shuts off your iteration history, and you need that for your homework because I ask you to give the -2 log likelihood to 3 decimal places. So if you had no it print on, it would shut off that table. So make sure that that option is not included. By the way, just as an aside, this name length one, this is designed to keep the names of your fixed effects from getting truncated. By default, it starts squishing them together and cutting off some of the letters out of your variable names, which annoys me. So this just sets it to save it to up to 100 characters, which should be more than you should ever need. So make sure that this IC option is included in your proc mixed line. To use the fit test macro then, here's SAS. This is from example 3B, which you all have on the website for download. First of all, you need to have the macro read into memory. So that's just this little program right here. To use it, you need to put in 2 pieces of information, or what are known as arguments to the function more generally. These are names that I've created, fit fewer and fit more. These are the names of the InfoCrit table for the nested models you're going to compare, where fewer refers to the one with fewer parameters and more refers to the one with more. So the -2 log likelihood should be bigger for the one with fewer, it should be smaller for the one with more. So then when you want to use that, for instance here, I save from the empty model, I save the InfoCrit table to a data set called fit_empty. So the word InfoCrit, that is a SAS specific name. You have to say that. That's what it knows to refer to within its own architecture. fit_empty is my own name. You could name that Valentine's Day for all it cares. So long as you have no spaces in it, you can name it whatever you'd like. I tend to name my tables the first 3 letters referring to what kind of table it is, such as covariance parameters versus fit, and then some kind of label that tells me which model I'm on. So I have fit_empty as one model. I had saved fit_mood as a comparison model, for instance, and then you can do fit test by calling it the % fit test. Fit fewer equals the name of the table, fit more equals the name of the table with more stuff in it. And then you should get a little piece of output that compares the 2 and does your likelihood ratio test. If that isn't working for whatever reason, you can always use a spreadsheet to do the same thing, which I've also included in your download packet. There is a tab within the Excel spreadsheet for example 3B called deviance tests. and that is here. You can input your -2 log likelihood, your degrees of freedom, and it will compute the difference between the two as well as the exact p-value. So that's one set of questions. I sent out an email after class last time that I had screwed up the degrees of freedom in the answer key to the homework. When you add a random quadratic, please use 2 degrees of freedom to get the right p-value. That's question 17. It should be 3, but I screwed up and put 2, and so that's what the correct answer will be. So my bad. As it turns out, I am not perfect. I apologize. So any other homework or SAS questions that I can help you with? Nope. Okay, well then let me know if anything else comes up. I'll shut that off. And we have then some stuff for today, continuing on in the world of time varying predictors. So big picture, we're interested in making sure we represent all the sources of variance in all the variables of our model. So we've talked about this extensively with respect to outcomes that vary over time. What kind of variance do they have? At a minimum, we know that they have residual variance within persons over time, but they also likely have between-person variance in their intercept. How much is dictated by the interclass correlation. And they may have between-person differences in slopes for time as well as for time-varying predictors. So that same type of consideration, what kinds of piles of variance do we have in the outcome? We have to give equal consideration to what kinds of piles of variance we have in our time-varying predictors. I'm showing you the brute force way of separating those piles of variance into observed variables now. Later on, we'll do multivariate. So we did, just to review, person mean centering in our example last time. So to construct the variables then, we take the original time varying predictor, we compute its person mean across all observations for a person, we take that person mean variable and center it at a constant, so 0 is meaningful, and that goes in the level 2 model. So that represents the idea of being a person who tends to have more of the time varying predictor than other people. Trait type variance, if you will. At level 1 then, and this is where the distinction comes in. Today we're going to go show you the other way of doing business. I start with this one because this is my favorite for longitudinal data. This is the easier way, far and above for longitudinal data, I think, person mean centering. You take your level 1 variable and you get rid of all between person variance and the intercept from it by person mean centering. Take the original xti, time varying x, subtract out the person mean. That renders it orthogonal to the person mean. So the only variance that's left in the level 1 within person predictor is level 1 within person variance. Therefore, the only possible kind of effect it can have is the level 1 within person effect, just like we want. Likewise, person mean x, the only kind of variance it has is level 2 between person variance. Therefore, the only kind of effect it can have in the model is level 2 between person. So that's why I like doing it this way, is because it's really hard to screw this up. If you don't put in either of these predictors into your model, you are assuming that its effect is 0, the same as any other predictor that you don't put in a model. So we did an example last time. Do you remember the story? What were our variables last time? Negative mood, being grumpy. Is being grumpy bad for you? According to my simulated data, it is. Yes, it results in higher glucose the next morning if you are grumpier than usual within person's level 1. And if you tend to be grumpier than other people, you tend to have higher glucose overall than other people. So 2 different ways that grumpiness and, can I call it diabetic health? Can I say that? Is that okay, Amy? You're my diabetes expert. That's okay? Diabetic regulation? Tolerance? Okay. Okay, it's glucose. It's health something, except it's actually sickness because more glucose is bad. But I digress. So 2 different ways that those 2 variables can relate to each other, between and within. We carved up the time varying predictor so that each of those ways is represented by a separate variable. Okay, with me? Okay, now here's how the rest of the world tends to do it instead. I have had several people who took multi-level modeling from other sources say that those teachers told them that they found this group mean centering or person mean centering confusing, and so they do grand mean centering instead. So that's what I'm going to show you so that you can communicate with those other folks in their own language. What you're going to find is that it results in an equivalent model sometimes, and other times it results in an incorrect model. So there's your foreshadowing. So here's what our models, as we have specified them using person mean centering, tells us directly. It gives us an estimate directly of the between person effect. We can look at the reduction of random intercept variance at level 2 to see how to get an effect size for that level 2 between person effect. It also tells us directly whether or not we have a level 1 within person effect, and if so, we can use the reduction of the residual variance to judge the effect size for that. The third thing that you might want to know that these models, as specified with person mean centering, do not tell us directly via the model parameters is the difference between the 2. Now, just like any other non-direct fixed effect that is somehow still predicted by the model, I've already shown you how to get it. So for instance, in our first model we looked at with predictors of within person mood and between person mood, I added a line here to get the thing that I'm going to talk about next. It is a linear combination of the between and within. It is the difference between the 2. This third type of effect is a different kind of level 2 effect. It is called a contextual effect. Contextual effects in longitudinal data don't make a whole lot of sense, to be honest. They make a whole lot more sense when we get to cluster data. The idea of a contextual effect is whether or not the between and within person effects are of the same magnitude. That's statistically what it is. Conceptually, what it means is that there's an effect of between person variance over and above your current level on a given occasion of the time varying predictor. I know that's a mouthful, but it's the idea of, I'm going to have to make up a word here, of information being extrapolable. That's my new word, okay? Extrapolable. So if I give you a survey and ask you about your mood today, and you're like, today sucks, and I come back tomorrow and I give you the same survey, today sucks too, and you say that every day, there's a sense in which I could extrapolate that maybe you're a grumpy person because you said today sucked every day. So the contextual effect is, to what extent is this between person characteristic extrapolable from your level 1 within person data? To what extent do we need to know about your person mean over and above what you said each day in order to make an accurate prediction? If we do need to know over and above, then we have a contextual effect at level 2. Yeah. The ICC for the time varying predictor tells us how much between person variance we have relative to the total. This is a question of whether that between person variance has a differential effect than the within person variance does. So the ICC is a precursor to having to worry about this. If your ICC says you have some between person variance, then there is a potential that the between person effect is different than the within person effect, such that there is a contextual effect. Contextual means there's a difference. So it's easier to depict this with a plot, I think. Let me see if I can get to that. Nah, let's not do that yet. Let's just talk data. So this idea that the person variance contributes over and above the daily variance or the time-specific variance. That's contextual effect. That is what the level 2 effect of the person mean becomes if you switch your centering method at level 1. So this is the other way of setting up a time-varying predictor. It's called grand mean centering because most of the time people choose the grand mean for the centering constant. You don't have to. The key idea here, though, is that you are centering your time-varying predictor at a constant, not a variable. So rather than taking the person mean as the thing that's your level 1 variable is deviating around, it's just deviating around a number. It can be any number you want, including 0. You don't even have to center it, doesn't matter. So when you set up your level 1 predictor that way instead, what happens to your interpretation changes. So this is where it starts to get confusing. The reason why we get different answers for our parameters if you center at a constant than a variable has to do with whether or not those two predictors are correlated or not. So remember what I told you about person mean centering? The person mean and the within person variable are uncorrelated, right? So when you put them in the model at the same time, the effect of each is as it would be if the other wasn't there. They're not competing against each other. Each has its total effect at its own level. In contrast, if I just put this time-varying predictor in just like this, it still has its between-person variance in it. And that between-person variance is going to compete with the person mean. So if we go back to regular old regression, right? If I put in two predictors in the model that are uncorrelated, such as in person mean centering, each gets its own effect. If the predictors are correlated, when you put them together, they get a different effect than if they were in there all by themselves. They get their unique effect after controlling for the other thing. That's the language you learn in regression, right? The unique effect rather than the bivariate effect, uncontrolling. Same thing happens here. So here is an example, a data file, where I have two people, 2 rows of data for each people. My first person has a person mean of 3 for their 2 rows of data. My second person has a person mean of 7. So at level 2, to differentiate one person's trait on this variable from another, I would subtract their person mean x, subtract some constant. So for instance, if the sample mean was 5, I'd subtract 5. So I could say that the person who got a 3 on average tends to have less of this variable over time, whereas the person who got a 7 tends to have more of it. So far, so good. One way that a mean of 3 for the person could have been created is if they gave me a 2 on one day and a 4 on the other. Likewise, the mean of 7 could have been created by giving me a 6 on one day and an 8 on the other. This next column here under person mean centering, the purple, this is what we did first. We took that time varying variable and subtracted the person's mean from it, such that when the person who tends to get a 3 got a 2, they were 1 unit below, and when the person who tends to get a 3 got a 4, they were 1 unit above. And the same is true for the second person. So the person mean column there has only relative information in it. How absolutely high they are on X is gone. All we know in the person mean column is if they're higher or lower than usual. All we know in the person mean column is within person, level 1, relative to my own average variance. So then when we fit our models, this column right here, this person mean X centered column, this carries all of the level 2 between person information, whereas this within person X column carries all of the level 1 within person information. Neat and tidy, clean separation. If instead of within person X, we don't center at a variable, we center it at a constant, such as 5, here's the column we get left. So this column, which I am naming time varying X, it has both kinds of information in it. It still indicates whether one person is absolutely higher or lower on X, and it indicates whether they are relative to their own average higher or lower. It has both. So time varying X contains both level 1 variance and level 2 variance, whereas person mean X only has level 2. That means when you stick them in the same model, they're going to fight against each other, and their effects will be different when they're put together than they would be if they were kept in separate models. Okay, are you with me? So here's what happens. First off, this is the wrong way to do it. This is smooshing, and this is the thing that I will spend my life trying to prevent. Some people try to cure cancer or help kids with autism. I try to prevent smooshing. This is my cause that I am passionate about. And not the kind of smooshing about the Jersey Shore. I'm indifferent about that kind of smooshing. This is the kind that I care about. Yes, you can ask the Google later if you haven't already what that means. So this is what a lot of people think when they say grand mean centering. They think they're good because they have taken their time varying predictor and created a meaningful 0 point by subtracting off a constant. They put it in the model at level 1 and they're done. So because this time varying X still has between person level 2 variance in it and level 1 within person variance, putting it in the model as one parameter forces those two sources of variance to have the same effect. So this term right here, this gamma 1O, it's not between and it's not within, it's a smoosh of both. And if the word smoosh makes you uncomfortable, feel free to use other people's synonyms. Convergence effect, a conflated effect. Composite is another one, but that word is used for a lot of other things, so I don't like that as much. I would go with conflated or smushed, and conflated is a Chris Preacher word. Convergence comes out of the accelerated longitudinal designs literature. But the key idea here is that we're only allowing one parameter to do the job of what should be two. So in order for this to be okay, it has to be the case that the between coefficient would have been the same as the within coefficient. That never happens. The only way that could happen in terms of scale is if both the X and the Y had ICCs of 0.5, because then they could potentially be on the same scale with respect to their variances. Otherwise, this coefficient is a blend of the two that is uninterpretable. So that's bad. So if we go back to the picture that I had before, just to remind you what that looked like, here's my person mean centering picture, where I took my time varying X and I decomposed it into its level 2 box and its level 1 box, and each box gets its own fixed effect in the model. Instead, without the person mean as part of the model, you're doing this. You're saying that this variable, this X that is a blend of the purple and the green, has the same effect on the green as it does on the purple. That's what you're saying. Fortunately, whether or not this is okay is an empirical question. All we have to do is figure out whether the between effect is statistically equivalent to the within effect, and we're good. I've shown you one way to do that already, which is to ask SAS to give that to you as a straight up difference. So under person mean centering, an estimate statement that gives the within effect a -1 relative to the between effect a 1 can tell us whether or not the coefficients at the between and the within are the same number. So in our example, we had seen that the within effect was a coefficient of 0.01, the between effect at level 2 was a coefficient of 0.08, and that those two numbers were different by 0.07. That difference of 0.07 is not 0. So there's my test of whether or not it's okay to smush. Is 0.01 and 0.08 the same number? No. The end. That's my version of it. If you want the model to tell you that directly, then that's what grand mean centering can be used for, so long as you remember to put in the person mean. So this smooshed effect, then, what do you get? Well, here is a formula that I adapted from Radenbush and Breich that shows you the smooshed effect that you get is biased towards the within effect most of the time, because that's where most of the information is. In most designs, you have way more level 1 observations than you do level 2 observations. The standard error for the within effect is going to be smaller as a result, and so the blend that you get is going to be more heavily weighted towards within. So here's how you can ask the model to tell you whether or not smooshing is okay, how you can ask the model to give you the contextual effect directly as a model parameter. You put the person mean back in. So I'm using different colors here because this person mean X is now, even though it's the same variable, carrying a different interpretation. So let's go over what these variables are. Time varying X minus a constant, so it still has both level 1 within and level 2 between information in it. Person mean X is person mean minus a constant. That has only level 2. So if you think about putting these effects together and what the resulting unique effect is going to be, what does TVX have in it that person mean X doesn't? The level 1. So after controlling for person mean X, the effect of TVX becomes solely the level 1 effect, just like we want it to be. Rather than having it be solely the level 1 within effect because we carved up the variance that way, instead the model is doing it for us via statistical control. After controlling for the variable person mean X, the time varying variable at level 1 carries only the level 1 effect. So then it is unsmushed and it is okay. Yeah.
Those two C's should be the same.
They can be the same or they don't have to be. Or they don't even have to. The centering at a constant is just a shift in the intercept. It doesn't change any of the interpretation. Hey. Now here comes the tricky part. What the hell does person mean X mean? Because it's the part of person mean X that's unique, even though TVX already has person mean X in it too. And this explanation makes my head hurt, but it is what it is. It's the contextual effect. That coefficient for person mean X is the difference between the level 1 within effect and the level 2 between effect. It represents the extent to which the effect of being, say, a grumpy person is not directly extrapolable from having a grumpy day. See, extrapolable. Is anybody smarter than me have a better word? Verbal is not my strong suit. You may have guessed this by now. I thought of another one. Verboten. Verboten, that's what it looks like, right? Am I wrong? Is that French too? German. Okay, so the common denominator is that any word that is not strictly English, which is like all of them, I'm going to pronounce wrong because no one in my life would have said verboten correctly. It is apropos that no one said verboten correctly. So yes, extrapolable, okay? So the coefficient at level 2 represents the extent to which the effective person mean is not extrapolable from within person at level 1. So in the context of our example, this within person gamma 1O coefficient would still be 0.01, and now the 0.07 would show up here to get us to the difference to what it should be for the between. So in trying to depict this graphically, it looks like this. My time varying x at level 1, because we haven't subtracted out the person mean variance, is still both within and between. But now, because we've added the between part as a covariate, its effect becomes purely within. But part of the between effect is still within it. So person mean x comes in to pick up the remainder to get to what the full between effect should have been. I wish I were making this shit up, but I'm not. This is, didn't I tell you that this doesn't make any sense in longitudinal data? Now, if I told you that it makes a lot more sense in cross-sectional cluster data, would you believe me? I'll give you a very quick aside for when this does start to make sense. Let's say that we change our multi-level sampling design here. I'll do it in Excel so that everyone can see a little better, including folks who are playing along at home. So in our world, level 2 is people, right? And level 1 is time, right? You with me? Okay, that's our world. We're going to leave that world fairly soon. And we're going to switch to a clustered world for a day or two, in which level 1 is people and level 2 is group. Such as kids who go to the same school when you've sampled multiple schools. These same exact models, this exact same lecture, literally, I will give you again, except I will swap out the TI for IJ. Seriously, like it's a giant find and replace. So what I'm talking about there, if I were to do grand mean centering of a level 1 predictor would be a people thing, such as, let's go with SES and scholastic achievement. So generally speaking, if you are from a family with more money, you may have better scholastic achievement, right? No one knows why that is, but it seems to be that it is. Do you think it matters if you go to a rich school or a poor school? The idea that you need school mean SES then at level 2 is the same idea as what we're talking about as having like within person whatever and person mean whatever. So if I do grand mean centering in the context of this clustered example right here, I would say the level 1 effect of SES is the effect on scholastic achievement for that kid of having more money than other kids in the school. The level 2 effect then is after controlling for individual SES. What is the extra effect of the school's SES? What's the bonus you get if you go to a rich school? Because poor kids who go to a rich school get that same bonus. That idea of what is the effect of a group characteristic over and above the individual, that's a contextual effect. And that's why for clustered data, I tend to use grand mean centering for level 1 variables so long as you include the level 2 mean, because then you get what is the individual effect, what is the extra effect of the group after controlling for the individuals. I think that that makes sense in the context of clustered data because each of the levels are differentiable units. You can think about what a school is and school characteristics in the same way you can think about what a kid is and individual child characteristics. In the context of longitudinal data, though, you can think about people and their individual characteristics, but a time is not a thing, the way that a kid is a thing. So the idea that we would ask what is the extra effect of being a person with high whatever above and beyond the effect at this time doesn't make as much sense because after controlling for the time isn't a thing, the way kid is a thing. So these distinctions are an interpretation and conveniences to what you want to know. The good news is that they are linear combinations of each other. So you don't have to worry about it too much. And here is the math that proves it. And this is a well-known result in the context of fixed effects at level 1 and no interactions. So if you have a model where you have main effects at level 1 and main effects at level 2. The top of the slide shows the result from person mean centering. So if I create this variable within person X that has only level 1 variation in it, and I create this person mean X that has only level 2, I can rearrange that model to be equivalent to the model where I have the original time varying X and person mean X down here. So here's the mapping of the terms from one to the other. Intercept, same. Within person effect at level 1, same, so long as you have the mean of the person at level 2 included in both. What you get in level 2 is the difference between the two. If you use person mean centering, level 2 gives you the between effect directly. If you use grand mean centering at level 1, level 2 gives you the contextual effect directly. But you can go from one to the other. Within plus contextual is between. Between minus within is contextual. So this is to say that one model isn't right and one is wrong. They are equivalent. They are rearrangements of each other. The thing that's wrong is to not put any term in at level 2. That's the thing that's wrong. So long as you have a level 1 variable that has level 2 variance in it, and you put something in the level 2 model to account for that, you're gold. Jacinta.
Since the constant that you're using when you're doing grand mean centering isn't necessarily mean, right?
Yeah, whatever.
What are some common numbers that you use there?
The grand mean.
But, okay.
That's literally why it's called that, is because when some people, when you say the word center, they attach to it mean center, grand mean center specifically. Like that's what they think of when they think of centering.
Okay, so then what's the difference? Isn't that
The constant isn't on this slide because it doesn't matter. You can center it at 2,000 or 0. It really doesn't matter. It shifts the scale of everything over. The big difference is whether you're centering at a constant or a variable. When you're centering at a variable, you are splitting the variance out of the level 1 predictor. When you center at a constant, you are not. That's the big difference. So why this is really quite hella confusing is because it doesn't work like you would think it does in terms of what things mean. So if I go like this here, within person X equals time varying X minus person mean X. All right, that's person mean centering right here. Person mean centering at level 1 versus grand mean centering at level 1, which is just time varying X, and I'll put minus C because the minus C part doesn't really matter. Either way, I have the same level 2 term, which is person mean X, and then minus whatever constant, that doesn't matter either. So here are your choices. If you are doing person mean centering and you have just the level 1, let's say, I have a table in my book that has this shape, and this is very likely to be your quiz next week too in some permutation. So if I'm going to use person mean centering and I put in this variable, it carries the within effect. If I put in person mean centering and I put in just level 2, meaning I put in this one right here, it has just the between. If I'm using person mean centering and I put in both, this is still the within and this is still the between. And that's why I like person mean centering, because you can't screw it up. It is what it is, because you separated the variance into each level ahead of time. Contrast that with what happens under grand mean centering. So now I'm in this cell. These are the ones I'm going to use instead. If I put in time varying x all by itself, just at level 1, it's smushed. If I put in person mean x all by itself at level 2, it's between. If I put them both in together, the smushed effect gets controlled for the person mean to become the within effect. But the between effect also gets controlled for the level 1 variance to become the contextual. So the same two variables, even though it's the same term at level 2, what it means switches depending on what you pair it with at level 1. And that's why this is confusing, because level 1 works out to be the same either way, so long as you have controlled for the person mean at level 2. And this is why Chapter 8 is so long. Because guess what, folks? It's not just main effects, it's interactions too. If I have a time-varying predictor and I want to test a moderator of it, guess what happens if I put in my interaction by time-varying predictor all by itself? I create a smushed interaction. So in our example that we looked at last time, we tested a random effect of within person negative mood, found it was not significant. So we went ahead and tested moderation by gender of each of my two terms. So we saw whether the between effect of negative mood varied by gender, whether the within effect of negative mood varied by gender. Those are two different things. So when we do grand mean centering here, we're going to do the same idea. It's still two interaction terms. But what the between level interaction term means is going to switch to contextual rather than between. Okay. Questions? Okay, do you want to see the example? I think that might help, because you can see how the numbers rearrange themselves. So here's where we left off. Oh, I didn't cover this, but here's, if I had put gender on the class statement, this is what the same code would have looked like, just as an FYI. So here we're switching the variables that are included. So the models are going to start on page 8. This is example 3B. I will remind you how our variables were constructed at the very beginning. We're still going to be using person mean negative mood. The 0 value is already near the sample's mean. And now we're going to pair it with the grand mean centered version at level 1, which is time varying negative mood minus a constant. And I picked 0 because 0 is already meaningful. So that just highlights it doesn't matter what constant it is. So person mean negative mood is purely level 2 between. Time varying negative mood is both. Now let's see what happens. First off, I'm going to show you what not to do. So, okay, well, I'm going to put in time varied mood. It's a level 1 predictor, so I'm going to put it in at level 1. The end. What have I done? I smushed it. Is time varying negative mood a level 1 predictor? Yes, absolutely. But to the extent that it has between person variance, it's also a level 2 predictor. Does it have between person variance? It does. It's about 39% between. We already found that out with an intra-class correlation. So that 39% of time-varying mood has a chance to capture the between person variance in glucose, and the remainder, 61%, has a chance to capture the residual variance in glucose. So putting time-varying mood in only at level 1 forces the resulting coefficient to reflect both the level 2 between and the level 1 within simultaneously, which means it is going to be an uninterpretable blend of the two. So yes, once again, to encourage participation, you can feel free to read from the screen. You'll note that I have named my models Cope Smoosh and Fit Smoosh. So here's my coefficient. It's 0.01. I'm like, wait a minute, wasn't the within effect 0.01 before? Well, we have to get our decimals out. What was the within effect again from the original model of under-person mean centering? 01097. 01202. So it's a different 0.01. But this highlights the result that I showed you analytically. Whenever you fit a smushed effect, it's going to look a lot more like the within because that's where most of the information is. There is 21 days per person in this study, so there's a lot more days than there are people. And that's why the blend of the two is much more heavily weighted towards within. Here is proof that I've smushed, by the way. So if you're ever reading a manuscript and you're not sure if somebody's smushed, here are two ways to tell. Number one, if they have a table of fixed effects and you don't see the same words in the level 2 model as in the level 1 model. So if there's no analog at level 2 for the coefficient, they've smushed. If they report pseudo R-square effect sizes for a level 1 predictor in which the random intercept variance was reduced, they have smushed. So let me say that again. Let's back up here. Here's my two variance components, right? Un11 is my random intercept variance at level 2, right? It's between person differences in glucose, whereas the day one is residual variance at level 1. How can something that is measured each day capture person variance? It can't unless it's not only measured each day, but it's measured for each person, meaning time varying negative mood has person variance in it. That hidden person variance that we haven't distinguished yet is what is responsible for the reduction in variance at level 2. So that is proof, dare I say, of smooshing. So to recap, time varying negative mood, that variable, it was 39% between, 61% within. I fit it as a fixed effect in the model. That fixed effect is much more heavily weighted towards the within effect. But the fact that it contains between person variance is evidenced by the reduction in between person random intercept variance. The fact that it still does contain level 1 variance like we thought it did is evidenced by the reduction in the random or residual variance at level 1. So let's compare these effect sizes, because that's another point I want to make about why smooshing is problematic. It's not for the reasons you would think. Let me go back to what our pseudo R-squares were when we fit the model the right way. So our within effect should have been 01097. Our between effect should have been 08. That between effect of 08 should have resulted in a pseudo R-square of 0.033. In our current model, smooshed, what does this model say the between effect is? What does the model predict the between effect of negative mood to be? Same as within. Both of them are 0.01 according to this model. But we know the right answer is that the between should actually be 0.08. So what happens is that the effect size for the between is not as big as it should be because the between coefficient isn't being allowed to be as big as it should be. Instead of accounting for 3.3% of the random intercept variance, which is what the right answer is, our model only accounted for 0.9% because 0.01 for our level 2 between effect isn't big enough. So how do we fix it? How do we unsmush it, as it were? What do we add? How do we control for the between variance to differentiate these two types of effects again? Add the level 2, add the person mean back in, yep. And once again, feel free to read from the slide. So here's person mean negative mood back again. And now we have the exact same model as if we had done person mean centering because we have the construct of mood represented at both level 1 and level 2. And the level 1 effect is fixed. So the -2 log likelihood is the same, pseudo R-squares are the same, and the coefficients are rearrangements of each other. So after controlling for person mean negative mood, the unique effect of time varying mood reflects only its unique variance, which is level 1. So it becomes the within effect at level 1 like it should. What we get at level 2 is the contextual effect, the added effect of being a grumpy person above and beyond just having a grumpy day. That's labeled directly right here. To get to what the added effect is up to the total between effect, we add the contextual effect and the within effect together. In other words, here's my 0.01 for the time varying effect like it should be. Here's my difference of the between and within effects, my 0.07, my contextual effect. And 0.01 plus 0.07 gets me up to my 0.08 where it should be. And you can see that it worked by looking at the change in the variance components. By adding person mean negative mood at level 2, I have picked up another 2.4% of the random intercept variance, getting me up to the 3.3% I should have. I have picked up no more of the residual, because I haven't changed the level 1 model. Did I hear somebody whimper or start to ask a question? Because either sound plausible right now. It was a chord? Oh, even the equipment is whimpering? That's a new low. But yes, so the problem with smooshing is that you think you're interpreting a level 1 effect, but it's actually level 1 and level 2 together. Because it's biased towards level 1, though, you're probably underspecifying your level 2 model. So at the extreme, what if you had a negative level 2 effect and a positive level 1 effect? That could happen. If you smush them together, you could end up with 0. And you could end up with higher variance as a result of lower variance for fitting an effect in the wrong direction. Let me get you, yeah, this is the picture I want. So there was a paper I wrote with a colleague of mine, Rob Stosky, now at Oregon, called Persons or Contexts or something like that, which was trying to demonstrate these ideas in longitudinal data, because at the time we were tired of seeing people smush things in longitudinal data because it wasn't as well understood. And I had made a picture that looked like this, and the whole thing about the context was this vertical line, and in the published version of the paper, this line got left off, and I was so sad. So I make sure it's pointed out. It's the vertical line is the point of this picture, because you've already seen a variant of this picture before. But this is the best way I can get you to appreciate what the difference is between these two types of level 2 effects. So on the x-axis is time varying something. It can be negative mood, right here it's stress, whatever. Separate lines for separate people. The blue person has a person mean stress of 6, the green person has a 5, and the red person has a 4. So the person mean between effect, the total between, the effect of being a grumpy person, that is conveyed by the slope of the yellow line through the person means. For every unit more grumpy you are than other people, your outcome goes up by 2. That's the slope of the yellow line. Within persons, for every unit more grumpy you are than your usual, so moving along each of these lines, your outcome at that occasion goes up by 1. Or excuse me, it goes up by 0.5 in this picture. My bad, 0.5. Now you can see the slope of the individual lines is a lot less steep than the slope of the yellow line, right? So if I had only fit the predictor at level 1, it would try to kind of smush all of those different slopes into one, and it wouldn't fit. Much like the age convergence models. Remember that picture when you don't control for cohort effects? That's this again. It's the same idea. The vertical line gives you the context effect. So if I anchor here on a 5, right? A 5 was present in each of these fake people's data. The extent to which the person mean matters over and above the 5 is the slope, if you will, the vertical distance of this vertical line. That's the contextual effect. So after controlling for your absolute amount of the time-varying predictor, what is the extra impact of the person mean? The extra is the vertical shift along that line, and it's a slope of 1.5 per unit person mean. So either way, if you put the person mean in at level 2, you get the slope of this within person line at level 1. Good. If you're using person mean centering to do it, the level 2 coefficient is the slope of the yellow line. If you're using grand mean centering to do it, the level 2 coefficient is the slope of this vertical line instead. And I know slope of vertical line is a little bit squishy, but you know what I'm saying? It's like that's what this vertical distance is, what the black line is trying to convey. Because in this picture, there's more to the story than just getting a 5. It matters what your other data were, your other days had. The effect of being a grumpy person is not just extrapolable from any one day. How are we doing? What's your take home? This is a good example of where I want you to not necessarily retain the nitty-gritty, but to retain the big picture. What's your take home? Don't smush. And what is smushing? Giving the between and within the same effect. Any variable that goes in your model as an outcome or a predictor, you have to figure out what kinds of variance it has in it and let each of those kinds of variance have its very own effect. This is one way to accomplish that. This way is going to be insufficient if the time varying predictor has systematic differences in change, random differences across people. Because then you have to be able to unsmush what you're calling within, which is time varying, from between person in the time slope 2. And that's the point at which making boxes in this univariate approach is insufficient. You need a multivariate model at that point. So let me show you the interactions part of the program here. I tested a random effect of time varying negative mood. It was not significant. I then added interactions with gender and time varying negative mood and person mean negative mood. So I am allowing the level 1 effect of negative mood to vary by gender, and I am allowing the level 2 contextual effect of negative mood to vary by gender. And if I add this interaction term to that one, I end up with how the between effect varies by gender. So that's where you get all of this code here. The model directly gives you within at level 1 and contextual at level 2. You add them up to get to between at level 2. And you can get to the exact same set of results as the person mean centering model. So when I say don't smush, I mean don't smush your interactions either. That's the hard part. I have a bunch of more derivations as to what to do with interaction terms after this, but you can check out the math and believe me or not. Intravariable interactions is covered in chapter 8, I think, too, and that gets a little bit heady. Yeah, and there's some words. See? Words. Note the words are not necessarily corresponding to the order of the models. What I did is the same thing that I did in the book, which is to try and present all 3 effects that you might care about simultaneously, even though any one model only gives you 2 out of the 3. So I talked about the level 1 within, I talked about the level 2 between, and then I talked about the difference between the 2 as contextual. So you can get all 3 of them from either way. What else do I want to hit in here? Oh, random. Let me fast forward a little bit here, because this is a point that I want to hit. Random, slide 36. So it turns out that all of those equivalencies with respect to the fixed effects only hold if the level 1 effect is fixed. It does not hold exactly if it's random. And that's because here, under person mean centering, the variance that is related to the person mean is subtracted out of the random slope, whereas it is not under grand mean centering. So the variable that the random slope term, the U1, applies to is not the same across models. So that means that they are not equivalent and one potentially might fit better than the other. You can use AIC and BIC and maximum likelihood to decide. There is some anecdotal evidence given in the Radenbush and Breich book, and I did a little simulation that actually found the same effect here, that when you have a choice to make, when you're interested in random slopes, that person mean centering, or what they had as group mean centering in their context, will give you bigger variances. So let me explain this a little bit here. Let me go back to this one. The idea of centering. So when you have a random slope, your random intercept changes its interpretation, right? It's not person mean differences, it's person mean differences specific to the slope predictor being 0, like at time 0, right? Remember? Remember? Here, picture time. This is my best random slopes picture. Intercept variance, if time 0 is here, is this set of differences. If time 0 is out here, it's that one. So the random intercept variance is conditional on the 0 value for any predictors that have random slopes. Grand mean centering and person mean centering differ in how they define what 0 is at level 1. Under person mean centering, everybody has a 0. Under person mean centering, 0 means you're at your average. So that is within the span of everyone's data because we've defined it that way. Everybody has a chance to show being a 0 because it means I'm where I normally am. Under grand mean centering, not everybody gets to be a 0. If somebody is high all the time, 0 may be outside of the scale of their data. Likewise, if they're low all the time, 0 is outside. So to the extent that the interclass correlation for the time-varying predictor is large, people differ a lot from each other in their average levels, some people's extrapolation to 0 may be larger than others. To the extent that there is more extrapolation required to get to where you should be at 0, that random intercept variance is less reliable, and that lesser reliability can then propagate to the random slopes. So they have a little picture in their book that I've stolen. This is from Radenbush and Breik, where they're talking about here are different estimates for level 1x when we have defined it using, hang on, the, starting to lose my words here, grand mean centering, where some people, like if your data is out here, where you would be by the time you get to 0, the algorithm is going to be less sure about than if all of your data are aligned relative to 0. So if, to the extent that the random intercept variance is less credible, the random slope variance can get shrunken, and that's what they found in their little toy example. The random slope variance was bigger when you used person mean centering for the level 1 slope than when you used grand mean centering. So that is to say, since we're winding down here, big picture time, don't smush. Okay, that means that any predictor in your model, you have to figure out ahead of time what levels it has variance at and put in some kind of representation of that predictor at each level it has variance at. Same is true if you want to test interactions, so don't smush main effects, don't smush interactions. Each of those separate predictors for each separate pile of variance has a potential to interact with other stuff, and that means a lot more interaction terms. And if you have a choice to make, I would go with person mean centering for this reason and because it's damn easier. Because you can't screw it up.